Hello, everyone. This is Hal Tasaki. Welcome to my online lecture. So here I assume that you're familiar with basics of quantum spins, but let me just start by reminding you of a very interesting basic fact about quantum spins. Okay, so this is my basic notation for a single spin operator, XYZ component, the commutation relation, and S squared is equal to this one and this spin quantum. This is spin quantum number, which can take the value 1/2, 1, 3/2, and dot, dot, dot. And now, this is an important unitary operator that rotates the spin state by angle theta about the alpha axis, okay? And if you set theta to be 2 pi, 360 degrees, and then you know that this rotation operator equals the identity if the spin quantum number is an integer, but it's minus the identity if the spin quantum number is a half-odd integer. So this relation plays fundamental role throughout this lecture. And this may sound a bit weird because usually a 2 pi rotation doesn't change anything. But it's not always the case. Probably you know this. I hold him like this and try to keep him upright like this, always upright, and make a 2 pi rotation. This is 2 pi rotation, and you see a twist in my arm. So I make another 2 pi rotation. This is 4 pi in total, and then everything returns to the original state. So that kind of thing happens. Okay, so anyway, let's move on to our main topic. Okay, by Lieb-Schultz-Mattis type theorem, I mean a no-go theorem. I mean a no-go theorem that says that certain quantum many-body system cannot have a unique ground state with a non-zero energy gap, okay? And this statement, or this kind of theorem, is very interesting because it shows that symmetry of a quantum spin system puts a strong constraint on its low energy properties. Okay, and here in this talk, I concentrate on quantum spin chains. That means I have a chain, one-dimensional system with sites like this, and sites are labeled by integer, which is denoted by j, j plus 1, j minus 1, dot, dot, dot. And on each site, I have a quantum spin. It doesn't look quantum, but they must be quantum spin, okay? So this is our setting. Okay, part one is about the original Lieb-Schultz-Mattis theorem, okay? So the original theorem is about anti-ferromagnetic Heisenberg chain with this very basic Hamiltonian, okay? And I think the notation is standard and clear. And by EGS, I denote the ground state energy. Okay, the theorem works for half-odd integer spin, and it states that for any lowercase l, which must be smaller than this total system size, I had to say this L is the length of the whole chain, and I take periodic boundary condition. If I meet L plus 1, I identify that with 1, okay? L plus 1 is equal to 1, periodic boundary condition, okay? So this lowercase l is anything which is less than uppercase L, and then they prove that there is an energy eigenvalue E which satisfies this inequality. This means that, of course, E is an excitation energy and it's larger than the ground state energy. But this one here, since lowercase l can be made as small as, can be made as large as you want by making, first of all, uppercase L, the system size large, and again, also making lowercase l large. This quantity here can be made as small as you want. So this means that there is an excited state with whose excitation energy can be made as small as you want. So this should suggest that the system is gapless. I will come back to this point. But anyway, this is the theorem. And I didn't say C is a constant, and if you like, it can be written this way. So let me explain how they prove this theorem. Okay, the starting point is something called Marshall-Lieb-Mattis theorem, which states that the ground state of H is unique for any finite system size, which must be even. Okay. And by using this uniqueness, we first make an interesting variational estimate. First of all, we note that the uniqueness of the ground state and also the rotation invariance of Hamiltonian implies that the ground state is rotational invariant, or we say U1 invariant, because this one here generates a group U1. So this means that here we have this rotation operator of the whole spin chain by angle theta. And so this says that the ground state is invariant under any uniform rotation. But that is not what we're going to make use of. We shall make use of gradual non-uniform rotation or twist defined by this unitary operator here. Okay, and this is also spin rotation operator, but this rotation angle theta depends on the site. Okay, and well, it looks like this picture. It starts from 0 and gradually increases to 2 pi and stays there. Well, 2 pi is the same as 0, and this more explicitly, this rotation, site-dependent rotation is written in this way, or if I write this quantity delta theta, it's this. Okay. So let me write it again. So this is the twist operator, the same thing with this delta theta. And look, this delta theta is actually a small quantity because as I said, we want to make this lowercase l as large as we want. So delta theta is a very, very small quantity. Okay. Now, then I actually Bloch did very similar thing much before. But anyway, we define the variational state by this. So we just apply this twist operator to the ground state. So what happens to the ground state? So this is our ground state, and this is site 0, and this is site L. And then we make this gradual twist in this region of the ground state. So outside this region, basically no change, then things changes here. So let's take a site J here, site J somewhere here, which in this modified region, and look at this expectation value of the local energy. Then, of course, this local energy roughly should look like this. So it should take the minimum value. It should take the minimum when delta theta equals 0, because we have the ground state at delta theta equals 0. And since everything should be analytic in delta theta, we can say that this expectation value is basically the ground state energy density plus something proportional to the square of delta theta. Okay, and square of delta theta is of course equal to the square, basically proportional to 1 over L squared. Okay. And now, as I said, in this part, the ground state is modified, so this expectation value changes. But outside this region, like here, there's no change. So this expectation value stays the same as the ground state. So we find that this 1 over L squared modification takes place for like L bonds. So I multiply this by L to get this estimate. So, well, this is a bit sloppy way of explaining things, but this can be made rigorous. So we have this, oops, I erased this by mistake. We have this bound, but note that we haven't used the fact that S is a half-odd integer, and at this moment, this is valid for any spin quantum number. But we're not done. We still have to be sure that this new state psi L is what? This twisted state psi L is different. Psi L is different from the ground state, very much different from the ground state. That's the orthogonality estimate. So let's suppose that L is even, and we define a new unitary operator R by this defining equation. This is simply a combination of spatial reflection about the site L over 2 and the rotation of spin, pi rotation of spin about the x-axis, okay? And then you can easily check that the ground state is invariant under this unitary operator. And since the ground state is unique, we see that ground state should act like this. So if you apply R to the ground state, you get plus or minus 1. Okay. Now, this is our twist operator. And by simply combining the definitions, you see that this is equal to this thing. And you can rewrite, actually, you can rewrite it easily like this. So this is UL times this factor. But now, this is our familiar factor. I think you remember this. And I think you remember him. This is minus 1 if spin is half-odd integer. So in this case, we can estimate this inner product of ground state, of the ground state and this new trial state. First of all, this is the definition of this psi L. And now I make use of this property of the ground state and write this as the var UL or ground state. This is because minus 1 squared it's 1. Okay, then I make use of this relation here, R dog UL. Oops, erased by mistake again. I use this relation here again, and then I can say that this is equal to ground state UL ground state. Oops. But now, since we see that this thing and this one is the same with minus sign, so this must be equal to 0. So we have shown that this inner product is vanishing, it's 0. Now we can complete the proof. So now this is the unique ground state of this Heisenberg Hamiltonian, and this is a twisted state, variational state. And then we have, first of all, we have this variational estimate, and then we have this orthogonality estimate. Then it's obvious from the variational argument that there exists an energy eigenstate, whatever, psi tilde L, and whose energy eigenvalue satisfies this. So we are done. So this is the theorem. When S is a half-odd integer, there is an energy eigenvalue which satisfies this inequality for any lowercase l, which is less than the system size. Okay, here are 2 remarks. Now we have been talking only about large but finite system size L. What happens in the infinite volume limit? Actually, from this theorem, there still remains two different possibilities. One is that even in the infinite volume limit, the ground state is unique and there are gapless excitations. Or it may happen only from this theorem, this statement of the theorem, that there are multiple ground states. Some symmetry breaking, spontaneous symmetry breaking takes place and multiple ground states appear. And in this case, from beta ansatz and other study, we know that the first one is the case. So there is, in the infinite volume limit, there is a unique ground state accompanied by gapless excitation. And here, I also remarked that when s is an integer, we get no information from this kind of study. And in fact, if you study the Heisenberg, antiferromagnetic Heisenberg chain with integer spin, it is now known that the model has a unique ground state with a finite energy gap. This is a very interesting topic called the Haldane gap, but it's not the topic for today's lecture. Probably we can talk about it later. Okay, in this part two, I'm going to talk about something I call new Lieb-Schultz-Mattis type theorem. Okay, so the original, now this pointer works better. This original Lieb-Schultz-Mattis theorem had many extensions. This one is the original, this one is the extension for, the original one was for s equal 1/2, and this was extension to other filling, and this one is extension to higher dimension, and these are all very important extension, but one important thing is that all this extension relies on the U1 invariance, rotation invariance. More recently, there appeared some very similar no-go theorems for models with only discrete symmetry. And these are closely related to the trend in condensed matter physics called topological condensed matter physics. So these are the main papers, and actually this paper contains many, many results and extensions of Lieb-Schultz-Mattis theorem for quantum spin chain is only one of many results. Okay, so this is a typical theorem, which I call new type of Lieb-Schultz-Mattis type theorem. So again, we consider quantum spin chain with half-order integer spin, that's the same. And again, short-ranged translation invariant Hamiltonian, that is also the same. But new thing is now, I don't assume any rotation invariant, but we only assume invariance under, in this case, time reversal transformation. Time reversal means that simply you switch the sign of all the spin operators. And then if this is valid, then it can never be the case that the infinite volume ground state is unique and accompanied by a non-zero gap, the same statement. So I'm not saying that I'm going to study this Hamiltonian, but this is one example. Okay, so this is, okay, so this is an example of Hamiltonian which is not rotationally invariant, but it's time reversally invariant. Okay, so the statement appeared here. It was proved for matrix product states here, and the full vigorous proof was made by Yokata and myself. And this is the latest paper that I'm going to talk about. We have new general proof. But very interestingly, Matsui back in 2001 has essential argument for proving this type of theorem. He didn't prove this, but he already had the essential argument. That was very interesting. Matsui is a mathematician, and this is a very mathematical paper on quantum spin chains. Okay, so what is our strategy? Okay, so now this is based on our recent paper, this one in arXiv. So as for references and many details and things like that, you can look at this paper. And these are my two collaborators. Yoshiko Ogata, she's a mathematician. She's an expert in operator algebraic approach to quantum spin systems. And Yuji Tochikawa, he is a string theorist. Okay. And now, what is our strategy? In case of the original Lieb-Schultz-Mattis theorem, we studied spin chain with half-order integer spins, and we started from ground state, and we constructed low energy excited states rather explicitly. But here we don't do that. We start from the assumption that the model has a unique gapped ground state and try to look at a necessary condition coming from that assumption. And this strategy, so we are sort of reversing the logic, and this way of looking at Lieb-Schultz-Mattis theorem was, as far as we know, introduced by Masaki Yoshikawa in his very important paper. And the next strategy of ours is we make full use of something called the index for the edge state. We're going to explain, which notion was developed in the study of something called symmetry protected topological phase, usually called SPT phase. Good, so I will explain about this index carefully. I start from the notion of time reversal for a single spin. Okay. So again, this is our single operator for a single spin. And then time reversal is described by this map gamma, and which satisfies this one. This one I already said. So this is time reversal. So it should switch the sign of all angular momentum, and it should preserve the product and also the conjugation, and also it must be anti-linear. Alpha star, this is a complex conjugation, and this is not linear, but anti-linear. And this looks strange. This may look strange, but actually this anti-linearity is necessary. Why? Because these are spin operators, so they satisfy the commutation relation like this. Yes. So I want this transformation to preserve this commutation relation. And since we have 2s, this is mapped to this one, and this one is also mapped to this one. And now SZ is mapped to minus of SZ. So if this was a linear map, I goes to I, and we don't have the commutation relation that we want. But since this is anti-linear, we have minus I, and this we have correct commutation relation that we want. Okay, so this is the in mathematics this is called anti-linear star automorphism. But anyway, I think this definition is clear now, and also this is a unique definition. And now we want to consider the operator which acts on quantum state, spin states. And that is denoted by theta. And this is related to the this automorphism thing map by this relation as usual. And although this gamma was unique, I say that the choice of theta is not unique. And there can be several choices, but this is a standard choice. Now here theta is defined as the product of the pi rotation about y-axis and this operator called k. This is an anti-unitary operator, which is simply a complex conjugation operator. So here I use standard SZ basis for quantum spins and denote the spin state as a complex vector like this. Then k simply takes complex conjugation of all the vector entries. Okay, so be careful. This k, the definition of k depends on the choice of your basis state. That looks weird, but that is necessary. Okay, now I consider what theta squared is, and as you may guess, k squared is nothing, and you simply get this. And again, oops, you remember. So we have this thing again here. So this theta squared may be just identity or minus identity depending on spin quantum number. Here, by making use of this fact, we define something we call index. It's nothing really difficult. I simply write this relation like this with this I here, which may be 0 or 1. Okay. But this index can be added. Indices can be added. So suppose that you have one spin with index I1 and the other spin with I2. And if you think about the whole thing, then you can easily convince yourself that the index for the whole spin should be I1 plus I2. Of course, you take modulo 2, not 2. But this is, so 1 plus 1 is 0. Okay? So you can easily find this. If you want to know, what we are considering here is something called projective representation of the time reversal group. And this index is actually, in a more fancy word, it's an element of something called the degree 2 group cohomology, but don't care. We don't use this notion. We only use this notion of index here. Okay, so this is the index for a single spin. Here comes a very quick remark. There's something called Cramer's degeneracy, probably most of you know. If spin quantum number is a half-odd integer, then it can be easily shown that any spin state and its time reversal are orthogonal with each other. And suppose that your Hamiltonian is time reversally invariant, and suppose that phi is an energy eigenstate. Then by very standard computation, you can show that this theta phi is also the eigenstate of Hamiltonian energy eigenstate with the same energy eigenvalue. And since theta phi and phi are orthogonal, we find that any eigenvalue must be at least twofold degenerate. And so in particular, we see that this Hamiltonian cannot have a unique ground state. So this is nothing deep. This is only for a single spin. This is a very easy statement, but you can say that this is a kind of Lieb-Schultz-Mattis-like statement for a single spin. So we want to have analogy of this thing, which is valid for quantum spin chains, which have infinitely many spins. For that purpose, we want to consider index for edge states, and we start from an example. Okay, consider an infinite spin 1/2 chain. So it's infinitely large, and spin 1/2 is located on every site. And I take a very simple state called a dimer state, and this is a definition. It's very simple. J runs over even sides, and this even side J and odd side J plus 1 form a spin singlet like this, okay? And then you easily find that this whole thing is time reversally invariant. So this state on the whole infinite chain is simply time reversally invariant. But now I want to think about fictitiously cutting the chain into two and examine the transformation property of this part, this half infinite portion of this state, and how does it transform. And of course, in this case, there's nothing strange. We only have spin singlet, and spin singlet is the same as nothing, so this is invariant. Sorry. This is simply invariant under time reversal transformation, okay? But suppose, now this one was for J even. Let's suppose that J is odd, and you fictitiously cut the chain here into two parts, and you examine the transformation property of this half infinite portion of the state. And now, here you have extra spin 1/2, which forms singlet with this one, but we are looking at this portion. So this guy actually transforms as a spin 1/2. So from this observation, I say that this thing, in this case, this half-infinite portion of the state has index I, which is ij, which is 0, like integer spin. And in this case, this, this half-infinite portion of the state has index ij equal to 1, like half an integer spin. Okay, this was an example for spin 1/2, but let's look at infinite spin one chain. Now, if you have a spin 1 system, the basis state can be plus, 0, or minus. And this is a very simple state called a 0 state, which you have state 0 at each site, very trivial state. And in this case, again, you take this state on the infinite chain, and you fictitiously cut the system chain into 2 parts and examine the transformation property of this half-infinite portion of the state. And of course, in this case, nothing. You have nothing, and you have this index 0. And rather interesting. So actually, we are now looking at integer spin chain. And so you might expect that you only see something which is like integer spin, but it's not the case. Here's something called the AKLT state. And if you don't know about this state, well, you can just relax. And in this AKLT state, again, you fictitiously cut the whole state into 2 parts and examine the transformation property of this half-infinite portion. And then, if you notice the definition, actually these are singlet pairs, and if you fictitiously cut the AKLT state into 2, you see something called effective spin 1/2 edge spin, which is exponentially localized near this edge. And this is spin 1/2. So if you cut, you start seeing spin 1/2 degrees of freedom. So in this case, even though we are treating integer spin chain, we get index which is 1, like half an integer spin. Okay, these are just examples. And here comes a general result, general theorem. And actually something is wrong here. Oops. Okay, so now we consider general, very general, short-ranged, time reversally invariant Hamiltonian. That's the only assumption. I don't even assume translation invariance. This is the only assumption. And I also assume that the ground state, the Hamiltonian, has a unique ground state accompanied by a non-zero cap. That is the only assumption, okay? And here's this ground state on the infinite chain. Again, I fictitiously cut the chain into 2 parts at this site J and consider the transformation property of this half-infinite portion of the state with respect to the time reversal transformation. Yes. Then it was proved that there is a well-defined index, which I call ij, which is either 0 or 1. Okay, so it's we say that the game that we played for these states, like AKLT in these simple states, can be done for general unique gapped ground state. Okay, if you have time reversal symmetry. And here's another important thing. Okay, so you can cut the chain here and again examine the transformation property. In this case, you get another index, which I call ij plus 1. Now here, this ij is something very simple, which I talked before. This is an index. This is the index for the single spin which lives on j. So this one is something very difficult. You know, it represents the property of ground state on the infinite chain. But this ij, this is something very simple. If spin here is an integer, then this is 0. If the spin is half-order integer, this is 1. Okay. But anyway, both are the indices which characterize transformation properties with respect to time reversal transformation. They are the same kind, and actually, it was proved that they can be added. Okay, we have this identity. The identity itself is very natural. So ij characterizes the transformation property of this part, and this whole part may be regarded as a combination of this one and this one. So again, the index can be added. Of course, this is proved. This is not at all easy. This is very difficult. So here are some remarks about the index. So as for matrix product states, this index was introduced by Perry Garcia, Wolf-Sundberg, and Paul Montero, Belko, Shikawa in their study of symmetry protected topological phase. And indices for general unique gap ground state with symmetry this is actually based on very difficult mathematics. And there are many mathematical works, and I cannot list all of them, but these things by Matsui, Hastings, Ogata are very important recent things. And they are based on very difficult mathematics, like C-star algebra and so on. And, it looks like a magic. So this is a very strong statement, and mathematicians come and they say this is true. So, well, you can, in a sense, you can accept this as a magic. But this is a magic that you can learn if you want. So if you really sit down and study C-star algebra, split staging, type 1 factor, and then finally you understand everything. Everything is written in literature, but and more. You have to study more. You have to study books if you're not an expert. But anyway, everything is written down. But here we simply make here simply make use of all these results. Okay, so now here comes the proof of the new LSM type theorem for time reversally invariant spin chains. And actually the proof is surprisingly simple. So what we do is that we assume that there is a time reversally invariant unique gap ground state. That's what we assume. Then we don't assume, okay, that's what we assume. And then from what we said, this is our basic identity for indices, okay? So these are non-trivial indices for half-infinite portion of the ground state. And this one here, this ij is a trivial index. Now, we also assume that the system is translation invariant. Then it's very simple. Because there is translation invariance, this guy and this guy must be the same. And this means that ij must be 0. What does this mean? This means that spin quantum number is integer. Okay, so as I said before, I started from the assumption that we have a unique gap ground state with necessary invariance, and we arrived at this very important necessary condition. So from this fact, we see that if you have spin 1/2, if you have half-order integer spin, and then time reversally invariant, translation invariant, unique gap ground state is impossible. So we have proved this Lieb-Schultz-Mattis type theorem. Okay. This is very quick. So we used heavy mathematical tools, but the proof was just very quick. And now I can make use of the same strategy to prove a different type of Lieb-Schultz-Mattis type theorem for refraction invariant chains. So suppose that we have a quantum spin chain which is invariant under, again, time reversal, and also reflection about the origin. Okay. Now, okay, so this is our ground state, and as I said, if you cut it here, we can define index I0 here. And of course, you can look at the transformation property of this left half infinite chain, left half infinite portion of the ground state, and define an index. And since everything, the whole chain is time reversely invariant, probably it's natural that these two indices sum up to 0. This is minus sign 0, and this is proved. Okay, so this one is characterized by index minus sign 0. Now I use reflection invariance. Okay, so since everything is invariant under reflection about the origin, this portion and this portion must be identical. So this index here and this index here must be identical. Okay, now, then we are done. This is our basic identity, which I'm always using. And from this you simply see that I0 must be this. And then I use this identity to see that this is twice of I0. Twice of I, well, since in this world of 0 or 1, something is twice of I0 only when it is 0. So again, from the assumption that there is a unique gap ground state, I arrived at the conclusion that the spin at the origin is an integer. So this leads to the following LSM type theorem. You take a quantum spin chain now with site-dependent spin and short-range Hamiltonian that is invariant under reflection and time reversal. No translation invariance in this case, but only reflection invariance. And then, now the condition is given only for the spin at the origin. Then if the spin at the origin is half of the integer, then there can never be the case that the infinite Gaussian ground state unique and accompanied by a non-zero energy gap. So this is a situation. So now spin can be site dependent. It's 1/2 here, 1 here, 3 halves here, 5 halves here, 2 here, and so on. But everything must be invariant under reflection about the origin. So again, in this situation, we can prove this Lieb-Schultz-Mattis type theorem. And actually, this kind of theorem was, as far as we know, first found by Fuji in 2014, and also we found this in paper by Paul Watanabe and Zalto. Okay, so here comes the quick summary. So I talked about the original Lieb-Schultz-Mattis theorem, which is based on gradual twist based on the U1 symmetry. And I also talked about the new Lieb-Schultz-Mattis type theorem that follow from the properties of the indices for edge states. So the two leads to very similar statement, but the argument was very much different. And also this is a remark, the new result for this one extends to general symmetry group G. Then this 0, 1 is replaced by an object called a degree 2 group cohomology. Okay. If you don't know, just forget. Okay, so the lecture ends with an advertisement. So if you're interested in more background in related topics about quantum many-body systems, on my new book with this fancy cover, beautiful illustration, will appear very soon in June from Schrdingers. So if you're interested in, please look at this book. Okay, so that is basically all. Thank you very much for watching this. Goodbye.